All right, good morning. 13.3, we're going to talk about partial derivatives, which maybe sounds more complicated than it is, but basically what a partial derivative is, when you've got a function of more than one variable, you're taking a derivative with respect to one of those variables, okay? So for instance, let's just do example one real quick, and I'll show you how this works, and then I'll give you a couple examples of what this means. Say we've got a function, f of x, comma y, is equal to 3x minus x squared y squared plus 2x squared y. I'm sorry, I think that's 2x cubed y. Okay, so we can find a partial derivative with respect to x. We can find a partial derivative with respect to y. Okay, just real quick notation for partial derivatives. You could say df dx. Now, the book, they will use these little kind of cursive d's. I don't care if you call it just df dx. But you'll notice when the book is talking about partial derivatives, they'll use these little almost italicized d's, okay? Other notation is just f sub x for your x partial derivative. Sometimes they'll say f sub x at xy of xy. What else? df dx, that's about it. Or it could say like the d dx of f of x, comma y. Could say something like that. I think there was one more. Oh, it could just say dz dx. Could say z with the little x down there. So those all mean the same thing. Okay, just a partial derivative of your function with respect to x. Okay, so we'll just say the x derivative. Now, when we take an x partial derivative, it means we're holding every other variable constant. So we're treating y as a constant when we take this derivative. We're taking the derivative only with respect to x. Okay, so the derivative with respect to x of this thing is 3. The derivative with respect to x of this thing, we're treating y squared as a constant. So we get minus 2xy squared. Here we're treating y as a constant. So we get the derivative of the x cubed is 3x squared. The 2y is a constant, so we get plus 6x squared y. Okay, my y derivative. So that eraser is terrible. The y derivative is the y partial derivative. So we're treating x as a constant, so that goes away. Derivative constant is 0. The y derivative of this is going to be minus 2x squared y, and then plus 2x cubed. Okay, that's all you do. Now, to talk about what this means in context, so let's say this is a different book, but I really like this one because it gives, this is something called the heat index. Sometimes they're like, oh, it's 95 degrees outside, but it feels like it's 110 degrees. Okay, so they come up with this heat index. With the heat index is a function of actual temperature and the relative humidity. Okay, so something like if the actual temperature is 92 degrees, but the humidity is really high, the humidity is 85%, it's going to feel like it's 123 degrees. Okay, that's your heat index. Okay. Now, when you're taking a derivative, so we might take the derivative. Okay, your heat index I is a function of both humidity and temperature. So temperature and humidity. So you might take your heat and the rate of change of your humidity with respect, or the rate of change of your heat index with respect to temperature. Meaning, if I were to hold the humidity constant, how much does the heat index change as my temperature changes? So I would look at this row right here. I'm holding the relative humidity constant at 70%. But as my temperature increases, how much is my heat index increasing? Okay, so this is a way you could look at this with actual numbers. Okay? Now I could also take the rate of change of my heat index with respect to humidity, which means I'm holding my temperature constant. I might be looking at this row, holding the temperature constant at 96. But what is the rate of change of my heat index as my humidity increases? Okay? So you could find those things. Now, another way to see this, more visually with a graph, there's some really good pictures in your book. So if you look at page 895. So let's say this thing is my function of x, f of x, y. This is z is a function of x and y. So my z value here is the value of this surface. Okay. Now, if I'm taking the derivative with respect to x, that means I'm holding y constant. And so I can look at the intersection of my surface with the plane y equals y0 or y equals any constant. Okay. So basically what I'm doing, as x increases, so as x gets more positive, what is the rate of change of my z value of my function with respect to x? So as x changes. So my x derivative, so you can think of that as the slope, the rate of change in z over change in x. Okay. So it's the slope of this line being the intersection of your surface with a constant value of y. Okay. So it looks like right here at this point, my rate of change is negative. So as I move in this direction, my z value is decreasing. If I went to the back end, kind of over here, it looks like if I drew a slope there, that might be positive. That might have a positive slope back at the back end over there. Okay. Now, this one down here is another picture. Here's my x, my y, and as I hold, this would be to find a y derivative. So I'm holding x constant. So this right here, this plane right here is the plane x equals x0. So if I take the intersection of that plane with my surface, I get a curve. We're really finding the rate of change of that z value with respect to y as y increases. So at this point here, it does look again like the slope is negative. Okay. Example 3, there's a couple more pictures, which is kind of neat. So you've got this surface here, which looks like a paraboloid opening down. Actually, I don't, yeah, it's like a paraboloid opening down. Okay. So if I were to hold y constant at this y value, whatever that y value is, here you can see your plane, and the intersection would be this curve. So the rate of change of your z value with respect to x as you move in the positive x. So it looks like that slope is negative here. Probably when x was negative, your derivative of f with respect to x would be positive because this would be going upwards as you move in the positive x. This one right here, here you're finding the y derivative, so you're holding x constant at some x value. You can see this plane here. The intersection would be this curve. So your rate of change of z with respect to y at a given point, and you can evaluate that at a given point. Okay, so if you understand everything, that is perfectly fine. I'm going to go through a couple examples with you just in case. So let's look at example 2. Which my function is f of xy is equal to x e to the x squared y, x e to the x squared y. Okay, and it says find fx, the x partial derivative and the y partial derivative, evaluate each at the point 1 comma natural log of 2. Oops, you can't see that. That's better. So my x derivative, we can write df dx. You could write it as fx, either way. Now I have to use a product rule. So the first, x times the derivative of this thing. So that's the x derivative of this thing. So that's going to be e to the x squared y times the derivative of this, which is 2xy. Remember, I'm holding y constant. Okay, I can simplify that. at 2x squared y e to the x squared y. And if I were to evaluate this at the point 1 comma ln of 2, I would get 2 times 1 squared times ln 2 times e to the 1 squared ln 2. That's just a 1. So this thing just becomes a 2. This becomes a ln 2, and this becomes a 2. So I've got 4 ln of 2. Oh, I didn't do the second part of the product rule. So let's do that. Okay, so the derivative was this thing plus, sorry, I'm going to do the plus here. So this is the first times the derivative of the second, plus the second. So e to the x squared y. That's plus e to the x squared y. So this will be plus e to the 1 squared ln of 2. So that's just e to the ln of 2, so that's plus 2. Okay, so that's your answer for the x partial derivative valued at this point. Again, when you do the product rule, don't forget the second part of the product rule. And then let's find the y derivative. Okay, so the y partial derivative is equal to, this is a little bit easier because this is, the x is treated as a constant now. So we've got x times e to the x squared y, x times e to the x squared y times the derivative of the exponent with respect to y, so times x squared. So that's going to be x cubed e to the x squared y. Okay, and at the point 1 comma ln of 2, we get 1 cubed times e to the 1 squared ln of 2, which just gives you 2. Okay, so there's your y derivative. At that point. Okay. Now, one thing I do want to talk about that they talk about in the book is your definition of a derivative. So the definition, remember the definition of a derivative, df dx when you have a function of one variable is the limit as h approaches 0 of f of x plus h minus f of x all over h. It's the limit as h goes to 0. That was from last year. So the definition of a partial derivative, okay, and fx of xy is basically the same thing. It's the limit of f of x, you could call it h, our book calls it a delta x, comma y, minus f of x comma y. Notice nothing's happening to the y over delta x as delta x goes to 0. Okay, and your fy of xy is the limit of f of x. Now notice x doesn't change, but now the y, you're adding a tiny amount to the y minus f of xy over delta y as delta y goes to 0. Okay, so it's really the same definition of a derivative. It's just you're not, instead of adding your tiny amount to the input, to the overall input, you're adding that tiny amount to just the x value or to just the y value. Okay, so I think there is a problem or two in this section where you actually have to find, use this limit definition of a derivative to find a derivative. Okay, and I think that's all I need to go through right now. There are examples 3 and 4. I think they're pretty self-explanatory. They just word them a little differently. They say, okay, find the slopes in the x direction and y direction of your surface. Find the slopes. Well, the slopes are just the derivatives. So the slope in the x direction would be the x derivative at that point. The slope in the y direction of the surface would be the partial derivative with respect to y of your function. Then they word this one, find the slopes of the surface at given points. Okay, So those are good ones to do. That's all you're going to need to do today's problems. If you have any questions, again, we'll talk about again next week. Have a great weekend.